This video is just going to review the self-studies that I posted from my AP Physics 1 students to AP Physics 2 students to review for their exam. And this is just going to be some free thinking here just to help you get some ideas down well and quickly. So it could be a little bit more scattered this time. We'll see how it goes. So I've got a proton that's going to leave an electron, the negative plate, and then go to the positive plate. In order to do that, it must have an initial velocity, and it's going to come to a complete stop just before this plate. Well, there would be a voltage across the plate. I'll just label it V, and that's going to be called the stopping potential for that. So essentially, what do we have? Well, we have a kinetic energy conversion into electric potential energy, because it's all kinetic, and then it's going to slow to a stop here. So that's just going to be 1/2 mv squared equals qv. Now the charge multiplied by voltage is going to be electric potential energy. So that's what's going on there. And think of this as if I toss the ball upwards, I'm going kinetic energy to gravitational potential energy. And here it's kinetic into electric potential. Now what if I wanted the electric field between these two plates? Well, then I can just use volts equals ED. So the voltage across the plates is equal to electric field multiplied by distance. Okay, so there you go. Now remember, the voltage this time is called a stopping potential because it stops the proton, and of course it would fall back downwards to the plate if you let it go long enough. Okay, what about charges? Well, I've got 3 charges aligned up here, and let's say I want to find the force between these 2 charges. Well, that's just force electric equals kq1 q2 divided by r squared. I could find the force between these 2 charges as well, or I can find the force between the outside charges. Okay, now let's apply the superposition principle. I want to know the net force acting on the 8 microcoulomb charge. Well, we're going to receive a push this way. Let's call that force electric 1. We just pay attention to that one and pretend the green one does not exist. Now we can do the force electric 2 between these 2 charges, pretending that this one does not exist. Now, since all the charges are the same, the force electric between this one and this one here will be the same value but opposite. So this would have a net force of 0 newtons using the superposition principle. Okay, let's go on to hollow spheres. So I've got a metal hollow sphere conductor, and I want to know the electric field inside, anywhere inside this hollow space. And a reminder that electric field does equal 0 inside any of the hollow spaces there. So that's kind of easy to do. Now what if I want to know the potential difference between position B and position A? Well, potential inside, of course, is going to equal to 0. So how would I calculate the potential here? Well, I'll use volts equals kq divided by r. Now if I want the potential difference between 2 spaces, I'm going to take the volts here and minus the volts here, or vice versa. I'll start here and minus the volts there. Now remember, this is a negative charge, so we do have to put a negative in for the q. And what about the work done? If I want to take a proton from position B and then take it from position B and move it to the position inside. Well, work done, okay, by an electric field is also equal to electric potential energy difference. Okay, so electric potential energy for point charges is k q1 q2 divided by r. So I can calculate the work done here, and I can also, or the work, or the electric potential energy here, and electric potential energy here. Well, electric potential energy here is equal to 0. I could recalculate and figure out this one here using this equation. Or I can remember electric potential energy is just equal to Q times V. So I already have my voltage at this location and my voltage at this location here. So I can calculate the electric potential energy here, and this would be 0, of course. And then the difference between those two is going to be the amount of work done. Now, what charge is involved here? Well, let's say I want to move a proton, so that'll be 1.6 times 10 to the minus 19. Okay, and that's how you deal with work done, voltage, and electric field on point charges. What about the next situation here? I've got a mass that is suspended in midair because of the presence of another sphere here. Let's say they're both charged the same, so I give this the letter Q, this one the letter Q. Of course, this one may be positive, this one may be negative, and or vice versa, because they have to be attracted. Okay, so what do we have going on here? Well, we have force gravity downwards, and we have force electric upwards. We know those two have to equal each other. So if I want to figure out the value of the charges between these, I'm just going to say force electric is equal to K Q1, Q2 divided by R squared. Of course, these two are the same, and force electric is equal to gravity. So we're going to end up with mg equals kq squared divided by R squared. And that's how I can calculate the value for the charge on both of these spheres. Okay, moving right along. Now what if I have a box or a mass on a horizontal surface that's frictionless, and I want to calculate the maximum stretch if this box is charged and it's in the presence of electric field. Well, the maximum stretch, if I just let this thing go, it's going to move to the right. It's going to continue until the elastic potential energy is equal to electric potential energy. So we have two EPEs here. So that would equal 1/2 k x squared. Okay, and that's going to have to equal QED, because this is a constant electric field. So electric potential energy there is equal to QV, of course. But what's V? V is equal to ED. So if I substitute ED for there, I get QED. Now in this case, D is equal to X. So I would sub in X there. And of course, one X will cross off on both sides. So we'll be left with 1/2 KX equals QE. Now what about the equilibrium stretch? This is not the maximum. This is when force electric is equal to the force of the spring. Okay, so force electric is then going to be equal to the Q multiplied by E, and we'll set that equal to Kx. Now where does this equation come from? Well, remember, electric field equals force electric per charge. I take Q to the other side, I will have force electric. And then of course the force spring Kx, that is the Hooke's law K equation. Alright, so that does it for video number 1 for reviewing for the exam. I will then start the second video soon.